All right, let's jump right in. Today we're looking at an incredibly fascinating piece of scientific hardware. If you love understanding how things work from the inside out, you are absolutely in the right place. We're exploring size exclusion chromatography, or SEC for short, and we're going to break down the exact anatomy of this instrument to see how it achieves the seemingly impossible.
Think about this for a second. How do you actually separate macromolecules when your standard methods just completely fail? We aren't talking about your run-of-the-mill tiny chemical compounds here. We're talking about separating massive natural or synthetic polymers, the absolute heavyweights of the molecular world. When traditional separation techniques hit a wall because of the sheer size of these molecules, SEC steps in. It's an irreplaceable tool in the laboratory, but to use it effectively, we really need to understand its physical makeup. Okay, let's dive into this. Here's our roadmap for today. First, an introduction to SEC. Then, the traffic network analogy. After that, we're going inside the SEC column. Then, optimizing SEC efficiency. And finally, detecting the separation. Part 1. Introduction to SEC. Comparing size exclusion to the familiar. So when we compare SEC to a lab staple like high-performance liquid chromatography or HPLC, you'll notice they actually share a very similar mechanical foundation and methodology, but there's a glaring physical difference right at the heart of the machine. SEC requires columns with noticeably bigger volumes, simply to handle the sheer size of those macromolecules. Moving on to part 2, the traffic network analogy, visualizing the mechanics of separation. The mechanism here is brilliant. In SEC, the stationary phase is filled with pores of varying sizes. The biggest molecules are completely excluded from the pores. They just bypass them entirely. Meanwhile, the smaller molecules are small enough to penetrate deeply into that labyrinth of pores. To put that into perspective, imagine the molecules are vehicles and the pores are a city's traffic network. The large macromolecules, they're like massive transport trucks. They're way too big to fit down the narrow side streets, so they're forced to use the highway bypass around the city. And because they bypass all those tiny streets, they move much faster and exit the column first. The smaller molecules, on the other hand, are like little cars. They can turn down every tiny alley and side street. Because they explore all these small paths, they get delayed and take much longer to exit. It's an incredibly elegant, purely physical method of separation based entirely on size. Part 3. Inside the SEC column, engineering for resolution. Setting up an SEC instrument requires a pretty specific approach. Step 1, as we just mentioned, is utilizing those columns with bigger volumes to accommodate the macromolecules. Step 2 is honestly a brilliant engineering workaround. Since a single column's efficiency in SEC is often pretty far from ideal, it's customary to connect 2 or 3 columns in a series. By linking columns with different porosity characteristics, analysts can significantly increase the resolution of the separation. And step 3 is all about practicality. These gels and silica packings are sensitive, but hey, if they're handled with care, these column setups can survive and perform beautifully for many years. All right, part 4, optimizing SEE efficiency, pushing the instrument's limits. Now, to get the absolute best performance out of an SEC setup, you've got to control some specific variables. Using solvents with extremely low viscosity is absolutely crucial, as is conducting the analysis at high temperatures. The combination of low viscosity and high heat allows for the smoothest possible flow through that porous network. But here's a really fascinating quirk of SEC. Unlike other forms of chromatography where temperature drastically changes chemical interactions, in SEC, the retention factors, represented by K, are entirely independent of the temperature. The heat just helps the physical flow. It doesn't change the underlying size-based exclusion principle at all. And finally, part 5, detecting the separation, measuring the eluted molecules. So the crucial point here is how we actually measure the results once they exit the column. In SEC, the absolute most commonly used detector is the differential refractometer. As the solvent carrying the separated molecules exits the column, this device measures variations in the refractive index. And what makes this literally a game changer for SEC is that for polymers, this variation in the refractive index is usually entirely independent of the molecular mass. It provides a super clean, consistent baseline to detect exactly when the different sizes of our polymer have exited the setup. While the differential refractometer is definitely the workhorse, it's not the only tool in a box. Analysts will often use alternative photometric detectors alongside it. These include detectors operating in the ultraviolet, or UV range, and the infrared, or IR range. Rather than just giving a general signal that a molecule has exited, these UV and IR detectors are used to measure specific properties of the macromolecular solutions. So they add this whole extra layer of specific chemical identification right on top of the physical size separation. And that brings us to the end of our physical walkthrough. Just think about the incredible control this gives an analyst. How might manipulating that high temperature, linking a custom 3-column series, or swapping a refractometer for an IR detector change the outcome of your next chemical analysis? By really understanding the anatomy of the size exclusion chromatography instrument, you hold the keys to separating the giants of the molecular world. Thanks so much for joining me for this explainer. Keep exploring, and I'll catch you next time.